Welcome back. In the last few lectures we discussed compression refrigeration systems. So in this lecture I shall introduce another very important refrigeration system known as vapor absorption refrigeration system. So the specific objectives of this particular lesson are to introduce basic concepts of vapor absorption refrigeration systems, introduce simple vapor absorption refrigeration system, derive expression for maximum COP, discuss properties of ideal and real solutions, describe a basic vapor absorption refrigeration system with solution heat exchanger, and finally discuss desirable properties of refrigerant absorbent mixers. At the end of this lesson you should be able to explain basic principles of absorption refrigeration systems, estimate maximum COP of absorption refrigeration systems, differentiate between ideal and real solutions, describe the basic absorption refrigeration system with solution heat exchanger, and finally list desirable properties of refrigerant absorbent pairs. Let me give a brief introduction. Vapor absorption refrigeration systems belong to the class of vapor cycle similar to vapor compression refrigeration systems. Okay, that means they are just like vapor compression system, these are also vapor cycles. That means, as I have already explained, the working fluid undergoes a phase change during the cycle. So they are vapor cycles like compression systems, but there is one major difference between absorption systems and compression systems. What is the difference? Unlike vapor compression refrigeration systems, the required input to absorption systems is mainly in the form of low grade thermal energy. If you remember, in the compression systems the major input or the input to the system is in the form of mechanical energy to run the compressor. Okay, so that is you can call that as a work operated system, whereas in absorption refrigeration systems the main input to the system is in the form of low grade thermal energy or heat. That is why these systems are also known as heat operated systems or the thermal energy driven systems. Okay, this is the major difference between compression systems and absorption systems. These absorption systems are also widely used in various refrigeration and air conditioning applications. Since absorption refrigeration systems run on low grade thermal energy, they are preferred when low grade energy such as waste heat or solar energy is available. There are many industries and many situations where plenty of low grade thermal energy is either rejected, it is not used properly. Okay, in such circumstances one can use vapor absorption refrigeration systems by tapping the low grade thermal energies. A typical example is the waste heat rejected in many of the process plants, etc., or you can also use other low grade energy sources such as solar energy to drive the vapor absorption system. This is one of the main applications and advantages of absorption systems compared to compression system. That means you can use low grade energy sources. Okay, and since the working fluids used in absorption systems are mainly natural working fluids, that means you use either water or ammonia, which are natural refrigerants, these systems are environment friendly. Okay, these are two most important advantages of absorption systems compared to vapor compression refrigeration systems. So as I said, since conventional absorption systems use natural refrigerants such as water or ammonia, they are environment friendly. Now let us look at some basic concepts. The first basic concept is that when a solute, for example such as a lithium bromide salt, is dissolved in a solvent, for example water, the boiling point of the solution is elevated. Okay, this you can also state in another way. For example, if you are keeping the temperature constant and if you are dissolving the solute in a solvent, then the effect of this dissolving is to reduce the vapor pressure of the solvent below that of its saturation pressure at that temperature. This is the basic concept based on which the absorption systems have been built. Okay. So, now let us look at the most basic absorption system. In a basic absorption system, refrigeration is obtained by connecting two vessels with one vessel containing pure solvent. So, we call it as refrigerant, and the other containing a solution which is a mixture of refrigerant plus absorbent. At equilibrium, the temperature of the solution will be higher than that of the pure refrigerant. When the pressures are same, obviously as I have mentioned already, the temperature of the solution will be higher than that of the pure solvent. And if the solution is at ambient temperature, obviously the solvent, that means the refrigerant, will be at a temperature lower than the ambient. That means there is a temperature difference between the ambient and the solvent. So, this is the temperature difference using which you can produce a refrigeration effect. So, this is the basic principle. Now, let me explain this with this schematic. What I have shown here, let us look at the initial conditions. Initially, we have two vessels A and vessel B. Vessel A consists of pure water at 30 degree centigrade, and vessel B consists of a solution of water and lithium bromide, 50% lithium bromide by mass. Okay. So, one is a pure solvent, that is water, the other one is a mixture of water and lithium bromide salt. Let us say that initially the valve is closed and the entire system is in thermal equilibrium with the surroundings, which is at 30 degree centigrade. So, everywhere you have 30 degree centigrade in vessel B as well as vessel A, and vessel A and B are isolated. Okay. So, now what is the vapor pressure in vessel A and what is the vapor pressure in vessel B? If you look at the steam tables or steam charts, you will find that at 30 degree centigrade the saturation pressure of water is 4.24 kilopascal. That means the pressure inside the vessel A, that means this side of the system, is 4.24 kilopascal, which is nothing but the saturation pressure of water at 30 degree centigrade. Now, what is the pressure on in vessel B? Since in vessel B we do not have pure water, but we have a solution, obviously at the same temperature there will be a lower vapor pressure. And if you look at the properties of lithium bromide water solution, you will find that at 50% concentration and at 30 degree centigrade the pressure here is 1.22 kilopascal. These are the pressures at equilibrium conditions. Now, you can maintain the pressures at different values because the valve is closed. Now, let us say that we have opened the valve. Okay, come to this second part. We opened the valve. Initially, what happens, because of the pressure difference, the vapor flows from this side to this side, and since this solution, lithium bromide water solution, has an affinity for water vapor, the water vapor gets absorbed here. Okay, that means the water vapor is absorbed here, and the pressure tries to be same in both the vessels. Okay, so everywhere you have the uniform pressure. Now, suppose by some means we are able to maintain the concentration and temperature in vessel B. Okay, let us discuss how we can do this a little later, but for the time being, assume that we are able to maintain the composition and temperature. Then what will be the pressure in the entire system? The pressure in the entire system will be 1.22 kilopascal, which is decided by the solution, and this is nothing but the equilibrium vapor pressure at this composition and this temperature. So, on this side also you have 1.22 kilopascal. Okay. If you have 1.22 kilopascal here, what will be the water temperature? So, again if you look at the steam tables or charts, you will find that at 1.22 kilopascal this temperature at equilibrium is nothing but the saturation temperature corresponding to this pressure. That means, you will have 10 degree centigrade temperature in the vessel A. Okay, that means by having this combination and by opening the valve, I could reduce the temperature from 30 degrees to 10 degrees centigrade. Okay, and as long as you can maintain the conditions in B, the conditions in A can be maintained at 1.22 kilopascal and 10 degrees centigrade. Now, the outside temperature is 30 degrees centigrade and the water is at 10 degrees centigrade, and let us assume that we do not have we have diathermic valves, that means heat can be transferred from outside to the water. So, there is heat transfer from the surroundings to the water, and as a result of the heat transfer, the water will evaporate. Okay, and this vapor continuously flows from vessel A to vessel B, where it gets absorbed. Now, the absorption process is an exothermic process in this case. So, heat is released, and since we want to maintain the temperature at 30 degrees centigrade, this heat has got to be continuously rejected to the surroundings. That means, during this step what we are doing is we are adding heat at vessel A and we are rejecting heat at vessel B. and you are able to produce refrigeration effect here because you are able to transfer heat from the surroundings to a body at 10 degrees centigrade. Okay, that is how you are getting a refrigeration effect here. Now, if you have a finite sized vessels, let us say, that means A and B are finite sized, then you have a finite amount of water in vessel A and finite amount of solution in vessel B, and as a result of this water vapor transfer from vessel A to B, at a point may come where vessel A may become empty, or this may become saturated. Okay, that means once this becomes take the first case, when this vessel becomes empty means empty of liquid, then there will not be any more heat transfer because nothing can evaporate. Okay, so the refrigeration effect stops here. Okay, that means by this means whatever refrigeration effect you are able to produce, that is intermittent and it will stop after some point when you are using finite vessels. Okay, so this is the. So what we have to do to continue this process? To continue this process, what we have to do is we have to bring back this system to its original position. Okay. So how do we do that? We do that by regenerating the water vapor. Okay. So let us see what is the regeneration process. Okay. So this is this picture here shows the process of regeneration. During the regeneration process, what we do is initially we keep the valve closed and bring the vessels A and B. Vessel A and B again to equilibrium with the surroundings. So again everything will be at 30 degrees centigrade. Now open the vessel, open the valve and supply heat to vessel B. Okay. Now this due to the vapor transfer in the previous step, this solution is weak. That means it has more water vapor. Okay. So when you are supplying heat at a particular temperature Tg, okay, when you are supplying heat, then water is generated at this point, and this water vapor flows from this side to this side, and if you are able to keep this at 30 degrees centigrade, then the water vapor is coming here, it will condense at this pressure and at this temperature. Since this is an exothermic process, heat of condensation is rejected to the surroundings. Okay. That means during the regeneration process what we are doing, we are supplying heat at a high temperature Tg to the solution, so that vapor is generated and this vapor comes to the solvent side and it condenses by rejecting heat of condensation. Okay. So you are transferring you are reversing the process and you are transferring water from the solution to the pure solvent side. Okay. This process will continue till you get the required amount of water on this side. Okay. Then to complete the process, again you have to close the valve and bring both the vessels to equilibrium with the surroundings at 30 degrees centigrade. So the process continues. Okay. So one thing you can notice here is we have 3 temperatures here. One is the Tg, which is nothing but the temperature at which heat is supplied to the solution for regeneration. Okay. Let us call that as generator temperature Tg. Okay. And we have another temperature called the heat sink temperature, that means the temperature at which heat is rejected during absorption process and during the condensation process. Okay, T0. And finally we have the refrigeration temperature Te. Okay. This is the temperature at which refrigeration is produced. Obviously Tg is greater than T0 is greater than Te. Okay. This relation holds good. And now how do we decide the what should be this temperature and how much heat has to be supplied and all? That depends upon the temperatures, for example the amounts of heat transferred. These depend upon the properties of solution and the refrigerant and also the operating conditions. Okay. So this is the basic principle of a very simple vapor absorption refrigerant system. Okay. So to summarize, what we have done is we have taken 2 vessels. In one vessel we have kept pure solvent, and the other vessel we have a solution. Okay. So by manipulating the pressures inside by supplying heat or by rejecting heat, we could transfer vapor from the pure refrigerant side to the solution side during the refrigeration process, and from the solution side to the refrigerant side during the regeneration process. Okay. And during this entire process we could get refrigeration effect during one step, and we have to supply heat at high temperature during the regeneration process, and heat is rejected in both the processes of refrigeration and regeneration. Okay. So this is an intermittent system, that means you are not able to get refrigeration continuously. Okay. So you call this as an intermittent absorption refrigeration system. Okay. Okay. So as I said, you call this as an intermittent system. So with only 2 vessels, the refrigeration obtained is intermittent. So no refrigeration effect is produced during vapor regeneration. And these simple systems also have some applications. They can be used to provide refrigeration using renewable energy such as solar energy. For example, you would like to produce refrigeration using solar energy. Okay. So, you can have a very simple intermittent system consisting of these simple two vessels and with a valve and connections. Okay. What you have to do is, during the daytime when solar energy is available, refrigerant is generated, okay, and it is stored as pure refrigerant. Okay. During the daytime, it is the process of regeneration, and during night time what happens is surroundings become cool. Okay, then the process gets reversed because the solution becomes cool. So, the refrigerant in the vessel, pure refrigerant vessel, can boil by taking heat from the surroundings. Okay, that means you get refrigeration effect during the night, and you have to regenerate the refrigerant during the daytime. Such systems are very good for very remote and rural areas where you do not have any electricity supply, or you want a system which is independent of your grid power. Okay, such systems have been built and they have been used quite successfully in many remote areas. Okay, so they are known as intermittent absorption refrigeration systems. But in practice, in most of the applications we require a continuous refrigeration. Okay, when you want a refrigeration continuously, obviously you cannot use this simple system with two vessels. So, you have to do certain modifications. So, this brings us to a basic vapor absorption refrigeration system for continuous output. So, continuous refrigeration can be obtained with a modified system consisting of two pairs of vessels and additional components such as expansion valves and solution pump. So, you have to have, first thing is two pairs of vessels, that means you will have 4 vessels. In addition to that, you also have to have some additional components such as expansion valves and a solution pump. These systems are similar to compression systems. That means you get continuous output just like a vapor compression system, but there are two major differences. The major difference is the way the vapor is compressed. In a mechanical, it is mechanical compression in vapor compression refrigeration system. That means you use mechanical energy, supply the mechanical energy to the compressor and compress the vapor mechanically. Okay, so you call these systems are mechanical compression systems. Okay, and in case of absorption systems, you can call that as thermal compression. Okay, if you compress the vapor thermally. Now let me explain the basic system. Okay, so here you have the basic vapor absorption refrigerant system. So, you have a condenser, an expansion device and an evaporator, just like a vapor compression system. The only difference between vapor compression system and vapor absorption system lies in the way in which you have compressed the vapor from the evaporator. That means what happens from this point onwards. Okay. So, in vapor compression system what is done? This low pressure low temperature vapor is compressed mechanically. Okay. Mechanically it is compressed to high pressure, so that it can reject heat in the condenser to the external heat sink and it can condense and become a liquid. Okay. So, you call this system, as I said, as a mechanical compression system, whereas you can see that in vapor absorption system you do not have a compressor. Okay. In place of a single component compressor you have 4 components. One is generator, absorber, expansion device and a solution pump. Okay. So, the combination of these 4 components replace the compressor of a vapor compression system. Okay. So, now let me explain the working principle. Let us start again from the point at the outlet of the evaporator. We have low temperature, low pressure vapor at this point. Okay. It goes to the absorber. In the absorber, this refrigerant vapor comes in contact with the solution that is coming from the generator, that means this solution which is weaker in refrigerant. Okay, this is weak in refrigerant. When this solution is weak in refrigerant, it has the potential to absorb the refrigerant vapor. Okay, so when this refrigerant vapor comes in contact with this weak solution, then the vapor gets absorbed. Okay, since the absorption process is an exothermic process, heat is rejected to the atmosphere at temperature T0, and this is the amount of heat rejected during this process. Okay, so the weak solution and refrigerant vapor are combining, heat is rejected. So, as a result of this mixing, what you have is a rich solution. Okay, this solution is a rich solution. Rich solution means rich in refrigerant. Now, this rich solution is pumped to the condenser pressure using a solution pump. Okay, a solution pump is used to compress the vapor from the absorber from the compress the liquid from the absorber to the condenser pressure. Okay, and now at this point you have high pressure liquid. Now this high pressure liquid goes to the generator. In the generator, what is done is heat is supplied at high temperature. Okay, so when you supply heat at high temperature to the rich solution, refrigerant vapor is generated. Okay, so this refrigerant vapor at high pressure and high temperature goes to the condenser, where it rejects heat to the surroundings, condenses and becomes a liquid. Okay, and this liquid again expands in the expansion device. So you have here a low quality liquid vapor mixer at low temperature and low pressure. This enters into the evaporator, it takes heat from the surroundings, produces the refrigeration effect and becomes the vapor again. So that is how the vapor cycle is completed. Okay. So the only difference you can notice here is instead of compressing it mechanically, we have compressed it thermally. Okay. Now what happens to the solution? Here remember that we had a rich solution that is entering into the generator. So from that you have stripped off the refrigerant. So what you have is a weak solution. Okay. Now this weak solution is still at high pressure. Okay. So to complete the cycle for the solution, you have to reduce its pressure. So we use an expansion device where the liquid pressure is reduced to that of the absorber or evaporator. Okay, and then again it comes in contact with this vapor. So the solution cycle is also completed. So this process goes on continuously as long as you supply heat here, you reject heat at absorber and condenser, and you have refrigeration effect continuously. Okay, so this is the principle of a very basic vapor absorption refrigeration system. And as I said, you can feel the similarities. Just like vapor compression system, you have two pressure levels here, PC and PE here, PC and PE here. Okay. However, unlike vapor compression system, there are three temperatures here. In vapor compression system, we have only two temperatures. That is, this is the T naught is the heat sink temperature, and TE is the low temperature heat source temperature. Okay. Whereas in absorption system we have three temperatures. One is TE, that is the low temperature source, then T naught is the heat sink temperature, and TG is the high temperature heat source. Okay, from which you supply the heat to the generator. So this is a 3 temperature cycle, and vapor compression refrigerant system is a 2 temperature cycle. Okay. So the major difference is you have seen. Now what is the advantage of this? I mean, if you look at the components and the schematic, you will find that the vapor absorption system is a lot more complicated compared to vapor compression system. We had only 4 components in vapor compression system, whereas we had 7 components in vapor absorption systems. Okay. And you might have noticed that even though we did not use a compressor, we still used a pump in the vapor absorption system. Now the pump requires mechanical energy. Okay. So both vapor absorption systems as well as vapor compression systems both need the mechanical energy, one to run the compressor, and in other case you need it for running the pump. Okay. And in addition to that, you also have to supply heat at high temperature. Okay. Since mechanical energy is required in both the cases, what is the advantage of absorption system compared to compression systems? The advantage is like this. In the compression system, you are compressing a vapor. Okay, so the mechanical energy required to compress a vapor is quite large. Whereas in vapor absorption system, you are pumping a liquid, and the work required to pump a liquid for the over the same pressure difference is much less compared to the work required for compressing a vapor. Okay, this is the major difference. That means the amount of mechanical energy required in vapor absorption systems is very small compared to a vapor compression refrigerant systems. Okay. In fact, it is practically negligible when you compare it with the heat input. So that is why absorption systems are mainly called as heat operated system, because that is a major input is in the form of heat. Okay. How do we say that the energy required for compressing a vapor is much higher than the energy required for pumping a liquid? Because you have seen that the work input is simply equal to integral VdP and the V is nothing but the specific volume of the working fluid. In one case you have vapor which has a very high specific volume, that is why integral VdP is very high, whereas in absorption system you have a liquid with very small specific volume. So, integral VdP is very small, so the mechanical energy requirement is very small. Okay. So, this is the major difference and major advantage of absorption systems over compression systems. Okay. So, that is what I have mentioned here. Work input required to pump liquid solution is much less than the work required for compressing vapor. So, the mechanical energy required to operate absorption systems is much less than that required to operate a compression system. However, of course, you have to pay somewhere. So, what do you do instead of a mechanical energy, you have to supply a large amount of low grade thermal energy to operate the absorption system. And as I said, the solution pump work is often negligible compared to the generator heat input. So, if you are defining COPs just like the compression system, you can see that the COP of a compression system is defined as the refrigeration capacity divided by the power input to the compressor WC, whereas the COP of vapor absorption system you have two inputs and one output. Output is QE, input is the heat input QZ plus work input WP. And as I have said, WP is negligible compared to QZ. So, COP of absorption refrigeration system is almost equal to QE by QZ only. That means refrigeration capacity divided by the heat input to the generator. Okay. So, this is the major difference between again compression and absorption systems in terms of COPs. Since vapor absorption refrigeration system uses low grade energy as input, the COP of absorption system is generally much smaller than COP of compression refrigeration system. Obviously, if you are if you are comparing the COPs, you get much higher COPs in case of compression systems, okay, because the quality of the energy that you are supplying to the system is much higher. Okay, work is a high grade energy compared to heat. Okay, so the COPs are larger. Okay, but of course, comparing the systems based on COPs, you can also call the COP as a first law efficiency. Comparing the efficiencies based on COPs is not really justified always, because the quality is different and the cost is also different. Okay, that means comparing systems based on COPs is not fully justified, as mechanical energy is more expensive than thermal energy. Hence, sometimes what we do is we define what is known as a second law or exergetic efficiency to compare different refrigeration systems. And you will find that the second law efficiency of absorption system is of the same order as that of a compression system. Okay, that means if you are comparing the two systems based on COPs, then absorption system is definitely bad, because you get very low COP. But as I said, since the numerator and denominator are of different qualities, if you want to get the real picture, you must convert them into the same quantity. Okay, that means you have to convert the numerator and denominator in expression for COP into exergy, let us say, then you get what is known as second law efficiency or exergetic efficiency. When you are doing this, you will find that the COP of the exergetic efficiency of absorption system is almost same as that of a compression system. Okay, so it does not look so bad when you are looking at the exergetic efficiency. Okay. This you can also justify this in another way. For example, when you are talking about the COP of a compression system, what is the input? Input is the work mechanical energy. Okay, most of the times the mechanical energy is derived from the electrical energy. That means to run a compressor, you supply the electrical energy. Okay, and how do you get the electrical energy? Electrical energy is generated, let us say, in a thermal power plant. Okay, and typical efficiency of a thermal power plant could be about 40%. You are not really taking that efficiency into account when you are calculating the COP of the vapor compression system. Okay, if you take that efficiency also into account, you will find that compression systems are not so efficient compared to vapor absorption systems, or in other words, both are equally good or bad. Okay. Now, when we discuss vapor compression refrigeration systems, if you remember, how did we begin? We began with an ideal cycle. Okay, first we have defined an ideal cycle and we found what is the maximum possible COP of this cycle. That means we found the maximum possible COP of a compression system. Okay, and if you remember, it was the Carnot COP. Okay, that means the reverse Carnot cycle gives the maximum COP. So, first we obtained the expression for the COP of a reverse Carnot cycle, and then we obtained the expression for the COP is for the real cycles. Okay, and if you remember, I said that the objective of this is to compare how good is the actual cycle with the best possible or with the ideal cycle. Okay, so in case of absorption systems also, let us first look at what is the maximum possible COP. Okay, then we will move on to the actual systems. So, as I said, for compression efficient system, the maximum COP is given by Carnot COP, and Carnot COP, if you remember, is simply given by TE divided by TC minus TE, where TE and TC are evaporator and condenser temperatures. However, in simple absorption efficient system, we have 3 temperatures. So, when you have 3 temperature levels, how do you get the maximum COP? Okay. One thing is for sure that the COP will be maximum when the system is totally reversible. That means when you have an ideal vapor absorption efficient system where it is reversible internally as well as externally. Okay, that means a totally reversible system. So, the COP of ideal vapor absorption efficient system can be obtained by applying first and second laws of thermodynamics. Okay. So, what we do is we take a ideal system and then you apply the first and second laws of thermodynamics. Let me show how we can do this. Okay, what I have shown here is the basic vapor absorption efficient system. This is the absorption efficient system which is operating in a cyclic manner. Okay, you can see the cycle. And here we have 3 temperatures, as I said: generator temperature, evaporator temperature and the heat sink temperature. And this figure also shows various energy flows. Okay, for example, you take high temperature heat input QZ to the system near the generator, and this system takes low temperature heat input QE at refrigeration temperature TE, and it rejects heat to the heat sink, and heat rejection takes place at the absorber QA plus condenser QC. Okay. So, heat rejected is QA plus QC, whereas heat input is QZ and QE. QZ is at the generator and QE is at the evaporator. In addition to that, we also supply mechanical energy to run the pump, okay, WP. So, these are the total energy flows in a simple vapor absorption efficient system. So, if you apply a first law of thermodynamics, what is the first law of thermodynamics? If you remember, simply we have okay, and for the cycle the net energy change is 0 because the working fluid is undergoing a cyclic process. Okay. So, what is the energy change, cyclic energy change? You can simply write this as QE plus QZ minus QC plus A. QC plus A is nothing but QC plus QA, okay, plus WP is 0. This is nothing but this expression, where as I said QE and QG are positive because you are supplying them to the system. This is negative because this is the heat rejected from the system, and work input required for the pump is also positive because that is also supplied. Okay. So, whatever is supplied to the system is positive and whatever is rejected from the system is negative. Okay. So, this is how you get the first law of thermodynamics, very simple energy balance. Now, what is the second law of thermodynamics? We write the second law of thermodynamics in the form of entropy change. And if you remember, the second law of thermodynamics says that the total entropy change, that means the entropy change of the system plus surroundings, will always be greater than or equal to 0, and this equal sign is for completely reversible, if everything is reversible, and the greater than is for irreversible systems. Okay. So, this is the second law of thermodynamics, right. Now, let us write expressions for delta surroundings in terms of QE, QZ and QC. Now, what is the entropy change of the system? Obviously, entropy change of the system is 0, right. So, delta S system is 0 because the working fluid is undergoing a cyclic process. Okay, for delta S system is 0, right. That means ultimately the second law of thermodynamics when you apply to this simply becomes delta S total is equal to delta S surroundings, which is greater than or equal to 0. Okay. Now, as I said, delta F system is 0 because the system undergoes a cyclic process. Okay. Now, we write the expression for delta S surroundings. Surroundings means we have 3 temperature reservoirs. One is a low temperature reservoir at TE, the other one is at high temperature reservoir at TZ, and this is the medium temperature heat sink at T0. Okay. And what is the entropy change of these reservoirs? The entropy change of low temperature reservoir is this minus QE by TE, minus because the reservoir is losing heat, okay, and its temperature is constant. Okay, so delta S, if you remember, is dou Q by T, because your the reservoir is undergoing a reversible temperature change. So you can write this, and T is constant. So simply this becomes 1 Q2 or whatever it is, delta Q divided by the particular temperature. So when you are applying this to the evaporator, this becomes minus QE by TE. When you apply this to the generator, this becomes minus QG by TG, and when you are applying this to the heat sink, this becomes plus, because heat sink is taking the energy, and this energy is taken at temperature T naught. Okay, so this is the expression for the entropy change of the surroundings. Okay, now you combine the first and second laws, so you get this expression. Okay, this expression relates the QZ and QE. What we are doing is we are eliminating QA plus C by using the first law. Okay, so that is eliminated, and then you end up get this expression. Now if you are neglecting pump work, okay, that means you are neglecting pump work, and if you define COP as we have seen, COP is equal to QE divided by QZ. Okay, you will find that from this expression, COP of a vapor absorption refrigeration system is given by this expression. Okay, that means always less than or equal to TE divided by T naught minus TE into TG minus T naught by TG, where remember that TG is the generator temperature, which is the highest temperature in the cycle, T naught is the heat sink temperature, and T is the lowest temperature of the evaporator. Okay. Now for a totally, because we started this discussion with a view to find out the maximum COP. Okay, so as I said, maximum COP takes place when the system is ideal. Okay, and for an ideal system, entropy change is 0. Okay, entropy change of system is 0 for both ideal as well as real systems, because it is a cyclic process. So for an ideal system, in addition to this, this also should be 0. Okay, that means delta S surroundings for a completely reversible system is equal to 0. So if you are equating this from the earlier expression, you will get this expression. Okay, from this expression you get the COP for an ideal system. This is the maximum possible COP of any vapor absorption refrigeration system operating between 3 temperatures TE, T naught and TG. Okay. Now if you look at this expression, you will notice an interesting thing. For example, you take a look at this quantity, okay, and look at this quantity. This quantity, for example, looks like the Carnot COP of a vapor compression system. Okay, because if you remember, Carnot COP is simply given by TE divided by TC minus TE, where TC is equal to T naught in this case. So this particular quantity is nothing but the COP of a Carnot system. And what is this quantity? This quantity is nothing but the efficiency of a Carnot heat engine. Okay, so ultimately the COP of an ideal vapor absorption system is shown to be a product of Carnot COP into Carnot heat engine. Okay, that means you can show an ideal vapor absorption system as a combination of Carnot heat engine and Carnot refrigerator. Okay, so what you are doing is, this is the generator. Okay, you supply QG from the generator to a Carnot heat engine and produce work and reject some heat to the surroundings, and this work is used to run a Carnot refrigerator. Okay, so the same work is applied to run a Carnot refrigerator, and this refrigerator takes heat from the low temperature surroundings QE, and again it rejects the heat to the heat sink T naught, and the efficiency of this heat engine is nothing but TG minus T naught by TG, and COP of this Carnot cycle is, if you remember, TE divided by T naught minus TE. So the combined efficiency of this N combined is nothing but the efficiency of this multiplied by the efficiency of this, that is NE into COP R. Okay. So that is how you can split a 3 temperature refrigerant system as a combination of 2 temperature systems. So you can see that, so from this you can easily infer that the COP of an ideal vapor absorption system increases as evaporator temperature increases, as generator temperature increases, and heat sink temperature decreases. When generator temperature increases and heat sink temperature decreases, the heat engine efficiency increases. Okay. And similarly, when the evaporator temperature increases and the condenser temperature reduces, the COP of the Carnot refrigeration cycle increases. So, as a result of which the combined efficiency improves. Okay. So, if you want to have a very high COP of a vapor absorption refrigeration system, an ideal system, you have to operate the system at as high a generator temperature as possible, as high an evaporator temperature as possible, and as low a heat sink temperature as possible. Okay. However, you will find that the COP of actual systems will be much smaller than the ideal COP due to various internal and external irreversibilities. So, as usual you will find that all real systems will give COPs which are much smaller than the ideal system COP. Okay. This is mainly because of the irreversibilities. Remember that an ideal difference between ideal and real cycle is lies in the irreversibilities. Okay. So, in the real cycle you have irreversibilities both internal as well as external. Okay. For example, what are the internal irreversibilities? Internal irreversibilities could be pressure drop due to friction, it could be in this case irreversibility due to mixing, right. And the external irreversibilities are irreversibility due to temperature difference between the working fluid and the external heat sink or source. Okay. So, mainly the temperature differences. These are the different irreversibilities which are a must in a real system. Okay. So, as a result the real system COP will be much less than the ideal vapor absorbent refrigerant system COP. Okay. Now, let us look at properties of refrigerant absorbent mixers. The solution used in absorption refrigerant systems may be considered as a homogeneous binary mixture of refrigerant and absorbent. Okay. You have noticed that in the thermal compression part of the vapor absorption system we have a solution. Okay. A solution circulates through the components, and this what is this solution? This solution is nothing but a mixture of refrigerant and absorbent, and for simplicity we assume that it is a binary mixture and it is a homogeneous mixture. Okay. Now, depending upon the boiling point difference between the refrigerant and absorbent and the operating temperatures, one may encounter a pure refrigerant vapor or a mixture of refrigerant and absorbent vapor in generator of the absorption system. Okay. That means, while discussing the or describing the simple vapor absorption refrigerant system, I mentioned that in the generator you supply heat at high temperature and refrigerant vapor is generated. Okay. And that refrigerant vapor goes to the condenser, it gets condensed and all that. But in actual systems, depending upon the boiling point temperature difference between the refrigerant and absorbent, in addition to the refrigerant vapor you may also have some vapor of the absorbent in the generator. Okay. That means, when you are supplying heat to the generator, both refrigerant as well as absorbent may boil. Okay. That means, what goes to the condenser may not be pure refrigerant, but a mixture of refrigerant and absorbent vapors. Okay. Whether you have a mixer or a pure refrigerant purely depends upon the boiling point temperature difference between the refrigerant and absorbent. If you have a very high boiling point temperature difference, that means when the absorbent is non-volatile, then you will find that whatever is generated in the generator is pure refrigerant. Okay. On the other hand, if the temperature difference is not too high, that means absorbent is also volatile, then both will be generated in the generator. Okay. An example of the first case where you have a non-volatile absorbent is when you use water and lithium bromide. Okay. So, where lithium bromide is absorbent, it is non-volatile. So, pure water vapor is generated. Whereas, if you use ammonia water systems where water is absorbent and ammonia is a refrigerant, both water and ammonia may be generated in the generator. Okay. So, this is the difference between different refrigerant absorbent pairs. Okay. Now, properties of binary solutions are evaluated from pressure, temperature, composition data. So, if you want to find the properties, you have to specify pressure, temperature and composition. Composition of the solution can be expressed either in mass fraction or in mole fraction. Okay. So, what is mass fraction, mole fraction? So, mass fraction is defined as okay, mass fraction is also sometimes called as concentration of component 1. So, I1 is simply defined as the mass of that particular component divided by the total mass of the solution. Okay. That means, M1 divided by M1 plus M2. Similarly, mass fraction or concentration of component 2 is nothing but mass of that component in the solution M2 divided by the total mass of the solution. Okay, m1 and m2 are mass of component 1 and 2. So for a binary system, you can very easily show that xi1 plus xi2 is equal to 1 from the above expression. That means xi2 is equal to 1 minus xi1. Okay, so if you know the composition of one component, the composition of the other component can be easily obtained. Okay, now the composition in terms of mole fraction. So instead of talking about masses, we talk about the number of moles. So mole fraction of component 1 is nothing but the ratio of number of moles of component 1 divided by the total number of moles of component 1 and 2 in the solution. Okay. Similarly, mole fraction of 2 x2 is given by n2 divided by n1 plus n2, where n1 and n2 are number of moles of components 1 and 2. Okay. Just like the mass fraction, it can be very easily shown that x1 plus x2 is equal to 1 or x2 is equal to 1 minus x1. And another very important property as far as refrigerant absorbent pairs are concerned is what is known as miscibility. Okay. And miscibility is an important property, and it depends upon the operating conditions. That means under certain operating conditions, a refrigerant absorbent pair may not be very highly miscible, whereas at other conditions they may be highly miscible. Okay. So it depends upon the operating conditions. And generally refrigerant absorbent pairs must be completely miscible both in liquid as well as vapor phases. So that is how you choose the pairs, so that they get mixed completely and you get a homogeneous mixer. Now let us define what is known as an ideal homogeneous binary mixer. Okay. A solution is called as an ideal solution if specific volume of the mixer is equal to the sum of the volume of its constituents. That means let us take a binary mixer. I take component 1 and component 2. Component 1 has a specific volume of V1 and component 2 has specific volume V2, and I mix certain masses of these two components. You will find that the specific volume of the mixer is simply equal to the volumes of its constituents, sum of the volume of its constituents. Okay. Then during this mixing process, neither heat is generated nor absorbed. Okay. So this is another characteristic of ideal solution, and the mixer obeys Raoult's law in liquid phase, and the mixer also obeys Dalton's law in vapor phase. So these are the four conditions. They are not totally unrelated, actually these conditions are related, but these are based on these four points you can say whether a solution behaves as an ideal solution or not. Okay. So let us look at mathematically what do we mean by this. So condition 1 as I mentioned, the solution of the specific volume of the solution should be simply equal to the sum total of the specific volumes of the components. Okay. So this is the mass fraction of component 1 and this is specific volume of component 1, this is the mass fraction of component 2, this is specific volume of component 2. Okay. So the specific volume of the mixer is simply equal to this. This means the solution neither expands nor contracts, that means there will not be any volume change upon mixing. Okay. So this is for condition 1, and condition 2, the specific enthalpy. Okay. Since no heat is released or absorbed, it can be very easily shown that the specific enthalpy of the solution is simply equal to the weighted average enthalpies of component 1 and component 2. Okay. Xi1 and Xi2 as I said are mass fractions, H1 and H2 are the specific enthalpies of component 1 and 2 at that particular temperature and pressure. Okay. So the same thing can be written in this form. Okay, because Xi2 is equal to 1 minus Xi1. This is the condition, the second condition. And what is Raoult's law? Raoult's law says that for an ideal solution, the vapor pressure exerted by component 1 is simply equal to the product of its liquid phase mole fraction x1 is equal to liquid phase mole fraction. Okay. So it is a vapor pressure exerted by component 1 is equal to the product of liquid phase mole fraction x1 into P1 sat. What is P1 sat? P1 sat is nothing but the saturated pressure of this component 1 at that particular temperature T. Okay. So P1 sat is this. So the vapor pressure is given for component 1 is given by this, for component 2 is given by this, okay, where x2 is the liquid phase mole fraction of component 2. So, this is what is known as Raoult's law. Okay. So, if you know the composition and if you also know the saturation properties, you can find out what is the vapor pressures in solution. Okay. What is Dalton's law? If you remember, Dalton's law is for the vapor phase, and it says that the vapor pressure in vapor phase is equal to the mole fraction of component 1 in vapor phase into the total pressure P total. Similarly, the vapor pressure for component 2 is equal to the product of mole fraction Y2 into the total pressure. Okay. This is the Dalton's law. Okay. So, you can easily show that the vapor phase mole fraction Y1 and Y2 are related by this expression, Y1 plus Y2 is equal to 1, just like your liquid phase mole fraction. So, Y2 is Y1 minus Y1, and the total pressure is nothing but the sum total of the pressures exerted by component 1 plus component 2, okay, PV1 plus PV2. Suppose if you have a component which is non-volatile, let us say that component 2 is non-volatile, then Y2 is equal to, it's almost Y2 is equal to 0. That means what you have is only pure vapor, only volatile component boils off, and Y2 is equal to 0. That means Y1 is equal to 1. So, in such case, when you are clubbing Raoult's law and Dalton's law, you can very easily show that total pressure exerted is simply equal to vapor pressure exerted by component 1, which is equal to x1 into P1 sat. Okay. That means again, if you know the saturated properties for the volatile component, and if you also know the composition, then you can easily calculate what is the total pressure exerted. Okay. So, these are the ideal solutions. Obviously, the real solutions are not ideal solutions. A real solution either contracts or expands upon mixing. That means the specific volume V is not equal to Xi1 V1 plus Xi2 V2, and either heat is evolved or heat is absorbed upon mixing. That means the mixing process is exothermic, either exothermic or endothermic. That means H is not equal to Xi1 H1 plus Xi2 H2, but it is equal to Xi1 H1 plus Xi2 H2 plus delta H mix, where delta H mix is called as heat of mixing, which could be positive or negative. So, the difference between ideal and real solutions can be attributed to their deviation from Raoult's law. Okay. So, let me show that. So, what I have shown here is the mole fraction of component 2 versus pressure. Okay. When the mole fraction is 1 0 here, that means you have pure component 1, and here you have component 2. Okay. That is why the pressure here is nothing but the saturation pressure of component 1, and the pressure here is the saturation pressure of component 2. Remember that the temperature is constant here, and if the solution behaves as an ideal solution, you have this line, because at any point the pressure is simply equal to x1 P1 plus x2 P2. Okay, that is from your Raoult's law. But the real solutions will deviate either in a positive manner or in a negative manner. If they deviate from a positive manner, the actual vapor pressure will be larger than the vapor pressure predicted by Raoult's law. Okay, this is what you call as positive deviation. And if they deviate in a negative manner, you find that the actual pressure is less than the pressure predicted by the ideal solution. Okay, that is from the Raoult's law. Okay, this you call it as negative deviation from Raoult's law. Okay. The same thing you can also show on enthalpy chart. What I have shown here is only for the negative deviation. Okay. So, real solutions with negative deviation, because this is what you encounter in vapor absorption refrigerant systems. So, for real solutions with negative deviation, you will find that the delta H mix is negative. Okay. That means heat is evolved during the mixing process. That means this process is exothermic. Okay. And this straight line gives the enthalpy of an ideal solution, and the enthalpy of real solution with negative deviation will be less than this, because the delta H mix is negative. Okay. So, as I said, if the deviation is positive, then at a given temperature and composition, vapor pressure exerted is greater than that predicted by Raoult's law, and heat of mixing is positive, that means endothermic. For positive deviation it is endothermic, for negative deviation it is exothermic. So, the reverse is true if the deviation is negative. Now, let us look at simple vapor absorption refrigerant systems. A simple single stage vapor absorption refrigerant system consists of a solution heat exchanger in addition to the basic components. The solution heat exchanger improves the performance of the system by reducing heat input to the generator and heat rejected at the absorber. That means the only difference between the earlier basic system and this simple practical system is an addition of one component, that is called as solution heat exchanger. So, what we have done in this system is an extra component is added, this is called solution heat exchanger. What is the function of this solution heat exchanger? This solution heat exchanger preheats, okay, preheats the solution that is going to the generator by using the heat of the solution that is coming from the generator. So, you can see that there is a heat exchange between the hot solution coming from the generator and the cold solution that is going to the generator. So, there is a heat exchange, as a result QC reduces, this also reduces, okay. So, that is a function of the solution heat exchanger here. Rest of the components are same, okay. In fact, this figure is shown as pressure versus temperature, okay. They have, so, you can also see the respective pressures and temperatures on this diagram, okay. This I will explain in detail when we discuss the actual systems. Now, let me quickly look at the refrigerant absorbent combinations. The desirable properties are: the refrigerant should exhibit high solubility with solution in the absorber, it should be highly soluble in the absorber, and the difference in boiling points should be large, so that only refrigerant boils in the generator, okay. So, this is another desirable point, and heat of mixing should be small, okay. Of course, point 1 and 3 are contradictory, you cannot have both, okay. Then there should be no crystallization or solidification inside the system. We will see what is crystallization or solidification in the next class, okay. Then the solution should be non-corrosive and it should exhibit good transport properties, that means the thermal conductivity should be high and viscosity should be low. So, these are the desirable properties, and based on these desirable properties there are two most commonly used refrigerant absorbent pairs. They are water lithium bromide for large capacity air conditioning applications and ammonia water for large and small capacity refrigeration applications. So, we will be discussing these systems in detail in next 1 or 2 lectures, okay. And there are also other refrigerant absorbent pairs which are at research level, they are not yet commercialized, okay. So, basically the most important pairs as far as the commercialized systems are concerned are water lithium bromide and ammonia water pairs, okay. Now, let me quickly summarize what we have learned in this lesson. In this lesson basic concepts in absorption refrigerant systems are introduced and simple vapor absorption refrigerant systems are described, and expressions for maximum COP of an ideal absorption system is derived, and properties of ideal and real solutions are discussed, and finally we have listed desirable properties of refrigerant absorbent combinations, okay. In the next lecture I shall discuss lithium bromide water systems, okay. After that I shall discuss ammonia water systems, okay. Thank you. Welcome back. In the last lecture I introduced vapor absorption refrigeration systems, and I mentioned that the two most commonly used refrigerant absorbent pairs are those based on water lithium bromide and ammonia water systems. In the present lecture I shall discuss the absorption systems based on water and lithium bromide, and the specific objectives of this particular lesson are: introduce water lithium bromide systems, discuss property evaluation with the help of property charts, present steady flow analysis of the system, discuss typical problems associated with this system, and finally describe commercial systems. And at the end of this lesson you should be able to explain basic principles of water lithium bromide systems, obtain relevant solution properties using property charts, evaluate steady state performance of the system, describe practical problems, and discuss commercial system practices.